go ahead and omit that one. It means don't do it. Okay? So, let me tell you quickly about a titration. A titration is a process. It's a lab. It's the idea that you can take this big stick-looking thing called a burette. You can put some acid or some base in there, and then you can add it to an acid or base in here. So I can have this piece of equipment with base in it, maybe sodium hydroxide or something, and I can have this piece of equipment with acid in it, and slowly, I'm going to slowly add base to this acid. Well, as I slowly add base to that acid, what am I going to do to the pH? So the process of neutralization starts to occur, right? Because acid plus base is a neutralization reaction. But what's slowly going to happen to the pH? Is it going to go up or down? Up, because this is something that has a low pH, right? It's an acid, it has a low pH. And as I add this, it's going to get more and more and more basic, right? So that's going to be pH going up. You should be taking notes with me right now versus looking through papers. All right, so if I do that slowly over time, and I have an indicator in here, well, phenolphthalein is what color in a low pH? Clear. See how it's clear? Yeah, it's clear. So phenolphthalein does not start to change color until what pH? 9. Who else remember that? 2 people. That's great. Not a great percentage. So as you add the base and you add the base and you keep dropping the base, you're going to slowly get your pH approaching pH of 9. And that's going to be the indicator starting to change color. Well, when the indicator starts to change color, we call that the end point. The end point is when the indicator changes color. And if you've selected a good indicator, you've selected an indicator that's appropriate for that style of reaction, because acids and bases come in many forms, right? Strong acids and strong bases, they'll react. Their pH at the end point will be 7 because they neutralize each other at 7. But like a weak acid and a weak base may have a slightly different neutralization point, and a weak acid and a strong base may have a slightly different one. So we will determine strength stuff a little bit more later, but just in general, when the indicator starts to change color, we're going to call that the end point. Now, if you're on your first titration, basically what you're doing is this, there's a little piece of, like this burette, this thing's like $50, right, for the glass, which is the burette itself. I'll show you that word in a second. This little thing down here is called a stopcock. Okay, you twist it and it drops out little bits of like maybe a milliliter or half a milliliter at a time into the flask below. That thing's like $60 itself. Okay, so you twirl this and twirl it and twirl it and twirl it until you get the volume that you want. And you can see it says slow down, because as soon as you start to see like a little bit of hint of pink, you're like, whoa, I'm getting close to the end point, slow it down. So then you do a little quick flick of the wrist. I like to try to throw those in there. So this right here, you'll drop one little hanging drop and then it'll change light pink. So what happens is many times we're not just experienced enough, so we twist it and twist it and twist it and we overshoot. So overshooting means you've gone too far. Now it's like Barbie pink, it's magenta pink, and that's not good. You actually have gone, so you've surpassed the end point. So it's actually an idea of determining something about an acid-base mixture with color changes. So we'll set this up on Monday. You'll figure out kind of the flow of this as we go. But all this does have some stoichiometry and some math behind it. So that's what we're going to practice a little bit more today. So this is the exact process, and this over here says volume of sodium hydroxide added. You'll notice this is called a titration curve. Okay, so you see now we're getting more graphs coming into play. So this is a titration curve, and where am I starting generally in terms of pH? So I'm starting acidic, right? So I have an acid, and it's in the flask. And I'm slowly adding what to it? Base, 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 base. And then overall, I'm going to add a lot of base, and the pH actually gets up close to 12 and 14. So that's why the axis down here says volume of base added, or sodium hydroxide in this case added, because in this case, sodium hydroxide in AOH is what I'm slowly adding to this overall acid. And at approximately 40 milliliters of volume of sodium hydroxide added, so there's 40 milliliters, that right there is the pH that I'm now going to call the equivalence point. What was the other point I just said? End point. Those are the 2 points, and I don't want you to confuse them. End point, we said, was what? When the pH indicator changes color. Where does phenolphthalein change color? And you can see it on this graph here. pH what? You see right here, this is phenolphthalein, right? You can see it changes from clearish white to approximately pink, about pH 9. So the end point is here at pH 9. but I'm using an indicator that naturally changes that point. But where does my acid 100% get neutralized? By the base at pH 7 here, and this is called the equivalence point. So if I'd chosen a better indicator, my endpoint would happen exactly the same time as my equivalence point. But sometimes we have a very limited choice of indicators. So phenolphthalein is one we use quite frequently. Methyl red is another one, but look where it changes color, at like 5. So neither of those are ideal, but we can always make sure that if we're knowledgeable enough about the reaction, we can choose a better indicator. So the endpoint is where the color changes itself. The equivalence point, I'll write the definition on the next slide, but basically it's where the moles of acid equal the moles of base in this particular reaction. So if the base is sodium hydroxide here, maybe my acid is like hydrochloric acid. So the moles of sodium hydroxide would equal the moles of hydrochloric acid, making it overall neutral. Therefore, the pH in this case is 7. And I want you guys to tell me why the pH is 7. This is where your knowledge from yesterday comes in. What's my reaction here? I just told you the two reactants. Say again? Hydrochloric acid and sodium hydroxide. What does that make? NaCl and water, right? So yesterday we were walking through baby salt, right? Baby salt was made by parents, acid and base. Doesn't matter, mom, dad, whatever. What controlled the feature or the characteristic pH of the salt? The strength, the relative strengths, right? The relative strengths of these acids and bases. So what's the relative strength of this acid?
Strong.
How do you know it's strong? Because it's one of your 6 strong acids, right? What about this one? It's a strong base. And how do you know that? It's out of the 8 strong bases that makes lowercase b on the periodic table. So strong and strong neither win. So what do they make the pH of the salt to become whenever it's dissolved in water? It should exist as a neutral salt. And so what's neutral in the stance of pH? 7. So when this strong acid and this strong base came together, they made a product when mixed with water yielded a neutral solution. And guess what that is on this titration curve? The equivalence point, right? That's when these 100% reacted and only this exists. So you can almost think of it like a limiting reagent problem. So when moles of acid and moles of base are equal, that means that let's say I had 1 mole of this and 1 mole of this. If I have 1 and 1 and it's a 1-to-1 ratio and I react 1 mole with 1 mole, don't they both run out at exactly the same time? Okay, so they both run out. I'm only going to have this left over. With that being a neutral salt, that means the pH of that solution is 7. Now, what if I keep adding base and I keep adding base and I keep adding base, meaning I have more sodium hydroxide and this is just gone, I don't have any more of that. What's going to start to happen to the pH? It's going to go up, 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 and what do we see here? Past the equivalence point, what starts to happen to pH? I'm adding more base, I'm adding more base, I'm adding more base, and eventually it's going to kind of start to max out. But yeah, the pH goes up. Because after this point, my excess is my sodium hydroxide, and down here I had a lot of acid still, but eventually I used it all up at this point. So this actually does relate a little bit to, well, definitely to stoichiometry and a little bit to limiting reagent. Okay, so let's make sure we know what this is. All right, so this is what a titration's kind of more definitional information is. You can write this in your booklet or on a separate sheet of paper. I did have you guys draw the pH titration curve on the last page of your booklet, but you guys also can add more there. So it says volumetric analysis. So that curve I was just showing you had what on the bottom axis? Volume of base added. Now, the reason I'm saying base is because I'm going to stick with one example for now, but eventually I'll start to flip it to do acid added. So volume of base added. So I'm looking at the volume of a base. Now, I have to have a solution of said base, and solutions are always published with a specific concentration. So maybe I could say, oh, this is like 0.20 molar sodium hydroxide, because we are going to be using molar concentrations like we have in this whole week. So if I start you off with 0 milliliters of base added, I'm going to draw the picture as we go here. and this is how you guys are going to be setting up your experiment. This is my flask of acid. And I just have some acid in here, right? So I'm going to call it HCl. But here's the big deal. I don't know what the molarity is. It's an unknown molarity. Your job is to use your knowledge of this base and its concentration and the volume that's required to figure out the acid's concentration. It's your unknown. Got me so far? I'm gonna walk you through it, but this is the game we play. So this is our unknown, and so sometimes the word unknown is used, while other times the word unknown concentration can also be called the analyte, meaning we're analyzing that guy, we're analyzing this acid. So since I have the concentration of the base, that reactant would be called my known. So my known, in this case, is the base, or my unknown concentration is my HCl acid over here. Got me so far? Okay. Now, so just like, I don't know why we have to have 3 names for everything, but in this case, unknown being analyte is an alternate term. Known and standard are also equivalent. Also sometimes titrate, but we'll get there shortly. Just like in your cabbage juice lab, what did I call your standards? What were your standards? Not the kitchen. The kitchens were the unknowns. All the ones where I told you, this is the pH, right? 2 through 12. So the known, which is the standard, is one you know everything about. So you know the molarity and you know the volume because you can take it from a graph perspective. So as I have my acid, it's going to have a pH pretty low, like down here at 1. As I slowly add base, and so I'm adding like, 10, 20, 30, 40, or so forth. I'm slowly adding base. My pH is going to start to rise. It's going to start to rise. And eventually, once it gets closer to the equivalence point, the pH is going to jump. And that jump is actually because of the exponential nature of logs, and logs are base 10. So when you do negative log, or actually no, in math class you guys do like log base 10x, something like that. So that's the nature of it being exponential is why it jumps so quickly. And eventually the base will, now that it's in excess, will start to kind of simmer down and it will just kind of remain basic. That's approximately what a titration curve looks like most of the time. So it's going to end up here at pH like 13 or so, and in this case I have a strong acid, strong base. The pH that's the equivalence point should be right smack dab in the middle of this vertical section. So when you're looking at the equivalence point, the way you find it is you look at the vertical section. It's pretty vertical. You kind of just do like a little eyeball, like, it's about where it starts, about where it ends, and about in the middle of that is pH. If I'm close, it's not quite the middle, but I'm trying to indicate to you it's about in the middle of the vertical section. So that vertical section, you're going to cut in half, and that's going to be your equivalence point. And that equivalence point is what was the definition we just read down earlier? Yes, that is when moles of acid equals moles of base. Okay. So what you would do is you would look at the equivalence point pH, and that's kind of important, but more specifically, the most important piece is down here. It's like, what volume of base did I add to neutralize that acid? And that's where we get into our calculation perspective. Give me a thumbs up when I can move on. At least you understand how to kind of look at the curve and glean some information off of it. All right, so with every single question like this, and I actually printed out, no, I didn't. Did I? No, I sure did not. I might need to print those for you. I think we got that point. Yeah. Okay. I didn't print these out for you guys, but let's talk about the process first, okay? So whenever you're solving, like, calculation-wise for a titration-based problem, you'll always be given a known and an unknown. And with that, you'll be given some concentrations, meaning molarity, and some volumes, but not always all of them. So the process of solving these, and I kind of just made a flow map for you, but I think if I do an example, it makes a lot more sense. So work with me on the process up here, and I'll jump down here. Anytime you're ever given a standard volume, the volume of a standard, this is your known, right? Standard, aka known. What did I tell you always know about the known? It's molarity and its volume, right? You know everything about it. So when you're looking at this, let's say you pull the volume from either, you know, looking at a burette, you're like, oh, I titrated about 20 milliliters, or you look at a graph, you always have your volume, but you also have your molarity. So what do you normally do when you have molarity and volume of the same thing? You multiply them together and you get moles, right? So remember, molarity times volume will give you moles. That's old news. So that's what I'm saying here. You now utilize the volumes, the molarity and the volume, you get moles. Once you get moles of that standard, nobody cares about that. You know everything about it. You know the molarity and you know the volume. What you actually care about is the unknown. So how would you ever get from moles of something to moles of something else? So you have to have a balanced chemical equation and get that ratio, the mole ratio from the balanced chemical equation. Well, of course you would have a balanced chemical equation because we have a reaction. We have an acid plus a base, and you know how to solve for those. And so what style of reaction is that? Acid plus base reactions are what style? They're double replacement. You worked on that a little bit yesterday. Okay, so once you get to your mole ratio and you find your moles of your unknown, you can go anywhere from your moles of your unknown. You can either just take your, it depends on what the question is asking, of course. You can take your moles to grams using what? Molar mass conversion, which is old school for us as well. It's just our basic mole to mole, our mole relationships. Or I can have you take your moles and I can have you instead find molarity. Again, what's molarity? Moles per liter. So take your moles and then divide by volume to get molarity. So basically, you have two styles of questions. After you get your moles of your unknown, I can either ask you for grams of that or molarity of that. And sometimes I can ask you for volume, but if I do enough examples, you'll start to see how you're flexible in your stoichiometry. So stoichiometry is coming back right now. So that's kind of your really generic process. Let's do an example so you understand how to label, process information, and actually complete the whole thing. Okay. So on this question, let's just read it first and make sure we're seeing what I'm seeing. So a student titrates, so that's like the whole big glassware procedure, right? Student titrates 20 milliliters of a sample of solution of hydrobromic acid. The titration requires 20.05 milliliters of 0.01819 molar sodium hydroxide solution. What is the molarity of HBr solution? Do you see that these two right here go with sodium hydroxide? So since you know the volume and the molarity, what would you call sodium hydroxide? The known, or what's the other word for known? The standard. What would you call HBr? The unknown, or the analyte, because we're analyzing something about HBr, knowing its volume, but we don't know its molarity. So that's how you're interpreting that. So sometimes it's important to write that down until you get the hang of it. So first off, first step always, write down the balanced chemical equation. Let's do that first. Get me started, Avery. Look, who are the two reactants here? Hydrobromic acid and sodium hydroxide. John, pick up from there. You all should be writing this example down with me. Not optional. John, pick up from there. H2O, so there's our water, and NaBr. And that's us just doing a double replacement reaction, the plus and the minus, and then the plus and the minus, they just rearrange partners. Is it balanced? Yes, moving on. Okay, so step 2, ID the titrant and analyte. And I'm actually going to write this right above the reaction, just so I can kind of keep everything really well organized. Ashton, what was the analyte again? Who was the question? Who was the unknown? Right, so this is my unknown, also known as analyte. Like I told you, sometimes more names than necessary are used to describe the same exact thing. All right, and then now the titrant, I told you it would probably come up, but titrant also means known or standard. And who is that, Syrian?
Sodium hydroxide.
Sodium hydroxide. Okay, so that's our known. All right, and then my third step is just start the stoichiometry process, but many times you guys are like, how do I start? I'm going to tell you to start with the titrant, aka the known. Now, you know how we always write down our givens? We haven't done that yet, right? Now, I like to write the reaction out first, because as I write my givens, I'll write them underneath who they're pertaining to, and then it shows you kind of how to get started. So who does this pertain to? HBr. I have a volume of, and you don't even have to write V, might make you think of a different formula. I have 20 milliliters of HBr. Let me get my sig figs right, guys. Ooh. Okay, and the titration requires 20.05, and this is of the sodium hydroxide, 20.05 milliliters of sodium hydroxide. That is 0.1819 molar. What is the molarity? So that's my question. What's the molarity of HBr? So now I have all my givens written down, right? I don't even need my question anymore because I can solve from here. So you guys have your kind of general flow. What do I say you have to start with? Find the moles of the titrant or the known or the standard, right? So we're going to use what here? What two pieces to get to moles? Okay, thanks, Meredith. So the volume and the molarity, right? I have that. Let's just use it. Start me off. So I don't really like milliliters right now because I know that molarity is expressed in what for what? Moles per liter. So either in your head, take the milliliters to liters, or I can show that to you. What do you guys want to do? In your head. Okay, you can do it in your head. I love it when you guys respond because then it lets me know what you need. All right, so if you're trying to convert from milliliters to liters, you're thinking of how King Henry died. He died by drinking chocolate milk. So milliliters in a liter, there's a lot more. There's actually 1,000 milliliters in 1 liter. So that's me taking milliliters to liters. Or you can back the decimal up. How many times, Brandon? 3. So that's 0.02005 milliliters. And this is of sodium hydroxide. Okay, now I'm going to take my liters and I'm going to multiply by my molarity. Thank you, Meredith. So I've used this already. I'm going to use this now. How do I write that out here? Moles of what? Sodium hydroxide per 1 liter. All right, so essentially I have taken volume and I've multiplied by molarity. I now have moles. I'm not going to stop here. You can stop and chunk this into 1, 2, and 3 different steps, but it makes your life a little bit more long. So the milliliters here have canceled. The liters here have canceled. I am done. I've made it to moles of sodium hydroxide. What is my next step to get to the unknown? Right, balance chemical equation. What's this ratio? 1 to 1. I know it's 1 to 1. You're like, do we really have to write it? Yes. Because it's showing that you've transitioned from something that you know something about to something that you don't know something about. So this is going to be 1 mole of what? HBr over 1 mole of sodium hydroxide. So we've now officially converted to what? Moles of the acid, right? Moles of hydrobromic acid. Moles of sodium hydroxide canceled. Now the question is molarity, right? And I've used both of these, but have I used this yet? No. Okay, so I'm going to show you guys both ways. You can either stop here and get moles. Let's do that first. Stop here and get moles. So calculate. Yeah, Frank.
373.
I got 3647. 3647? Okay. I like to make sure I wasn't butterfingers on you guys. Okay, so this is moles of HBr, right? Double check where you went wrong. You must have just missed a number. All right, so if I have this many moles of HBr, how do I get that to look like molarity? What do I need to do mathematically? Divide by liters. Well, how many liters of that do I have? So the 20 milliliters is no longer useful, right? So you're going to back that up 1, 2, 3, and that's point. So I'm going to take that moles and divide by liters, so 0.020 liters. All right, and then tell me what you get from there. I'm going to round this to 4 right here. Okay. Molar HBr. We have solved for the unknown molarity. Go us. You guys are like, calm down. Whoa. keep it together here, okay? So what did we process? Let's just go back and make sure we're clear on the process. First step was what? Whoa. What do you got? What do we do first? We read the question and we wrote down the balance chemical equation. Right. Then we're like, write down our givens with the known, aka the titrant, aka the standard, and the unknown with our question, aka analyte analyte, that's it. So once we kind of figured out who we knew most about, we start with the one we know everything about, and we find the what? Moles of it, right? So now I had to manipulate volume to get it to liters first, and then use the volume and the molarity to get to moles. But once you got to moles of the titrant, or the known, how'd you get to moles of the other thing? The mole ratio, okay. Now here we just stopped and just took a breath. We calculated moles first, then we divided by liters to get to the molarity. But what we could have done up here, and I'll do this in a separate color, was, some of you guys are fancy. It's good to be fancy. You can take, instead of just setting it equal to the moles, you can just times it by 1 over that. So 1 over the volume in liters. So 0.02 liters, which is basically you're multiplying by the inverse versus dividing. Either way it will work because it's the same process. All right, let's look at another one. This one. You started. If you don't understand a word up there, let me know. The word assayed means to test, to analyze, to experiment. All right, please read the question and just go through your process one more time. Vinegar is basically a solution of acetic acid. So vinegar, so that's what it's saying. Vinegar can be tested, assayed is the word for tested, to determine its acetic acid content. So it's just saying you're looking at the process of determining molarity of acetic acid in vinegar. These are all acid-base reactions. What's the base? That's all one reaction. What's your acid? What's your base?
I thought it was.
Okay. Yeah, got it. variable process after you're given down. All right, so this is, minimal expectations. I think this is probably where you are or farther at this point. So you have your acetic acid plus sodium hydroxide yielding sodium acetate and water. That's a double replacement reaction. Once again, this is old news. You looked at it, you read your question, you saw that the question was asking about acetic acid given the 15 milliliters. It said determine the molarity of the acetic acid, so that's really my question. It's kind of hidden, but it's there. And then your sodium hydroxide milliliters and molarity are given. Again, that's your titrant, right? That's your standard. So you started off with this information, and most of you guys are probably moving the decimal back 3 places to get so 22.7, boom, 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 back 3, 2270 liters times the molarity, but broken into its units of moles per liter. And do label them, like you have to identify moles of what, because I will ask that. So that's your sodium hydroxide, word to moles. Now what do I do? Liters have canceled. Now what do I do? Say again, Isabella? Mole ratio. What am I looking at? My question's about acetic acid, so this one must be included. And the fact that I have sodium hydroxide, this also must be included because that's the only way you'll convert and get rid of it. So what goes on the bottom, Isabella? And then what on top? Okay. And then from this point, what were your 2 options for finding molarity? Syrian? Okay, so I can multiply by the inverse. So 1 is just the placeholder. And what am I putting down here?
0.15.
So this in its liter form, so back the decimal up, point. No, you're right, 1, 2, 3. Okay, so just make sure we know that we're pulling that from the acetic acid. So you can either just multiply by the inverse, so 0.0150 liters on the bottom, or you could have stopped here at moles and just simply divided at the end by liters of your acetic acid. And what did you guys get? I totally heard you. Sorry. Let me make sure that. Oh, no. Didn't mean to cancel that. Don't cancel. Okay, because you need your moles divided by your liters to give your molarity at the end. One more time, Syrian. Not 8. 0.8, right? 0.8, 3, 2, 7. Just take that 7 off. Okay, so 0.832 sounds great. Okay, and looking back, this should kind of make sense. Comparatively, I had 0.55 molar of this, right? I required 23 milliliters of it. How much of this did I require? Only 15. So who should be more concentrated if they're trying to neutralize each other? The acid should be more concentrated than this, because this required slightly more milliliters, whereas this required lower milliliters, so there's a balance. Yeah. 1 over right here, 1 over 0.0150 liters. So, this is a placeholder. So this is us multiplying by the inverse, which what we did earlier was, you guys can tell me how many moles this is? What's this times that? Give me moles. Loud and proud. This is moles of acetic acid, right? So if we went from liters, what'd you say?
It's moles of sodium hydroxide.
Yeah. I do believe you all, but the mumbles get me sometimes. I can't really hear you guys. Okay, so this is moles of sodium hydroxide, which is moles of acetic acid. So when you take your moles of acetic acid, you can either just straight up divide by the volume, being 0.015 liters, which will get you this, or you could have just multiply by the inverse. So this red and this blue is exactly the same process mathematically. All right, let's do another one, but I'm going to make you a solve for a different variable that you haven't yet, making sure you're comfortable with this. So let me see. Yes, number 2. Complete number 2. I should see you all working on number 2 right now. What are you starting with on this one? The balancing of the equation. Absolutely. Let's check this. What's barium hydroxide, Ari? Okay. Okay, keep going. Pause. This is where your mistake is. Barium charge is what? Everybody look over here for me. Did we get the reaction balancing equation correct? You got your 2s and 2s. All right, and then you write down your givens. Ashton's table, how did you guys get started here? Mathematically now. It's okay, improvise.
So, I converted the
I'm gonna pause. It's really hard to start with your unknown. Barium hydroxide is your unknown, right?
sorry, the hydrochloric.
Right, so you converted the volume to what?
No, I converted the milliliters to liters and then I moles. And I multiplied by the molar.
Okay, perfect. So your standard practice is always get to moles of your known, which would be, how many liters is that, Brandon?
That was 0.02.
There's your liters, milliliters to liters, and then you multiply by 0.20 moles of HCl divided by liters. All right, so then you got 2 moles of HCl, right? William, pick up from there. Moles of what?
So I have 1 mole of barium hydroxide.
So 1 mole of barium hydroxide to 2 moles of hydrochloric acid. We finally have a different ratio. Whew. Okay, so 1 to 2 ratio. Great. All right, so here's the funny part. You're actually solving for what in this case? Volume, which is kind of weird, right? But we've actually done this before. We did this with solution molarity, concentrations, and stoichiometry within like that style of question. So what does this guy right here actually mean? 0.12 molar. What's that mean? 0.12 moles per liter. Is that not just a conversion factor? It's a fraction, right? What can you always do with the conversion factor if you need to? Flip it. So what if I take that and put it straight there? Will the moles cancel? No. So if I put this exactly as it was, 0.12 moles over liters, would the moles cancel? No. So I can't put it that way. Instead, what am I going to do? Flip it. So what do I put on the bottom? 1,2 moles of barium hydroxide, because that's what that right there actually means, right? Barium hydroxide. And the 1 liter will go on top. Remember, the 1 is always we write with liter whenever we are writing it in terms of molarity. So now the whole shebang, let's make sure. Liters have canceled, moles of HCl have canceled already, moles of barium hydroxide can now cancel, leaving you with what unit? Liters. And how many liters is this? 0.01. Can I get a second on that?
Yes.
Thank you. So how many milliliters is that? 10 milliliters. 0.01 is what you guys said, right?
Yes.
Okay. Okay, so that's about the only weird variation you'll start to find. You'll see this one has like milligrams. You guys can convert milligrams to grams and go from there. So I'm going to have you guys switch modes for me now. Let's do... All right, we're going to switch modes. Pull back open your laptops, because I know that you guys have to practice with this, that you will just accomplish some on your problem set itself. We'll probably get about half of this done. It's going to be all right. We'll try. So go to my website.